Welcome to, okay, recording started. Welcome to everybody. My name is Yentl Swolfs. I will be chairing this workshop that is co-organized by Wisnom and Federico Paris on compression strength, how to measure that properly and which factors affect this. I will give a brief introduction now on how we will host this workshop and on the agenda. So I want to start off with sort of introducing the series. This is now the third series. We had one on definition and proper measurements of strength, for which you can watch the YouTube videos through the links here. We will share the slides afterwards, so you'll get the exact links. And then after that, we had one on UD tensile strength measurements and factors affecting it. And today, we will have one on compression strength, sort of as a follow-up of the UD tensile strength one. We are already considering the fourth one, which will either be on shear or on transverse tension compression or a combination. We haven't completely decided on that yet, but you will hear more from us on that in the coming months, probably. So the next thing is on the objectives. So the objectives with this workshop and also the previous ones is to raise awareness of the difficulties with, even though these are basic properties, they tend to be pretty difficult to measure in practice, and not everybody seems to be aware of that. But we also want to identify best practices in how these properties should be measured in ideal circumstances, and to identify next steps in developing better test methods and better analysis methods, and hopefully that we don't need these workshops anymore in the future, that everybody's aware of how these tests should be performed. Brief overview of the agenda. This is in UK time, so you are all in different time zones. So I'm +1 in Brussels time. You may be in another time zone, but after this brief introduction, we'll have the topic presentation, which will be handled by Wisnom, which is essentially a presentation of the paper that we shared together with our invitation. Then we'll have 5-minute presentations by 9 different speakers. Then we'll have about 20 minutes of panel member questions. So this is a discussion just with the panel members. After that, we'll have a 10-minute break. Then we'll have open discussion where all the audience members can ask questions. And then at the end, we'll have conclusions, suggestions for next steps, and we can also briefly touch on topics for the next workshop. And we will anyway finish at 5 o'clock. At that point, we will stop the discussions and let you go on with the rest of your day. Very brief overview of our presenters that we have here today. I will not go through that, but you will see them appearing in this order. And then finally, just a few ground rules. So you probably have seen that we are recording this session, so we will put the recording on YouTube afterwards. That seems to be quite successful because our previous recordings have already been watched about 500 times, which is a surprising number of views, I think, for such a specific topic. We will also share all the slides afterwards to all the people who have registered and are attending today. Then during the discussions, you can write questions in the Q&A or raise your hand. So this is only for the part after the break. Before the break, we'll only have the discussions between the panel members. You can also upvote questions. So if we have too many questions to handle, we may be more inclined to pick the ones that have been upvoted by a few other people. You are unfortunately not, it's not possible to use your camera unless we give you special permission. So if you do want to ask a question live, it will be primarily through the audio and not really through video. And if you want to use, if you want to say hi or have some general comments, not questions for the panelists, then you can use the general chat rather than the Q&A. There is one limitation that we have in Zoom, and we cannot fix that, is that you cannot see the participants list as an audience member. Only the panel members can see that. So if you do have questions live from audience members, we will try to make sure that it's also clear who is asking that question, what the name of that person asking the question is. That's the short briefing. So I will give the word to Michael now to present the paper.
Thank you very much, Yentl.
Yeah, go ahead.
Yeah, okay. So, give me a second. Okay, can you see that?
Yeah. And now in full screen.
Very
yeah,
good.
Perfect.
Okay, so yeah, thank you very much, Yentl, for kicking this off today. So I'm really pleased to have the opportunity to give this short paper, which we produced in advance of the workshop, to set the scene, really, and to raise some of the issues and put forward a few points which you can agree with or disagree with. And I hope that the speakers and indeed the audience will pick up on this, and we should have some interesting discussion. So, measuring UD fibre direction compressive strength and the factors affecting it. So, as Yentl mentioned, we had a previous workshop where we considered what the definition of strength should be, because that's not such an easy matter to define exactly what we mean by strength. And at that workshop, we proposed that the strength of a unidirectional composite should be considered to be the maximum stress that the material can sustain under uniform uniaxial loading. Other definitions can be quite ambiguous and more subjective. So often you will see some indication of initiation of failure well before the final failure, and the point at which that occurs is somewhat subjective. And sometimes you'll get a catastrophic failure. At other times, you'll see that it actually goes beyond the maximum load and continues to carry load a bit further. So we propose that the maximum stress is the least ambiguous measure of this strength. This, of course, can be applied to all the principal failure modes, and in this workshop, we're considering fibre direction compressive strength. So compression testing is very hard. That's the reason why we're having this workshop, to raise some of the issues and discuss them. Of course, there's a fundamental issue with compression in that we have to avoid buckling. And that's not as easy as you might think. If you do simple buckling calculations, you might think you've got plenty of margin, but when you take into account the nonlinear response in the fibre direction and the shear response, then the buckling stresses can be a lot lower than you might think. So that becomes a major issue. Although you can use anti-buckling guides, and we'll have some discussion about that a bit later, there's questions about how good a job anti-buckling guides really do. So to stop buckling, we need a very short gauge section, but if we have a very short gauge section, then we may have an ununiform stress. So there's a trade-off there. We can't really have it both ways. But whatever we do, unfortunately, we can't really avoid stress concentrations. And you see this little schematic at the top right, where showing what happens when you have a tab and a specimen. And at that point there, you get high stress concentrations close to that tab point. And also you get high shear stresses where the load is introduced. And these mean that typically you will get premature failure, and these tests will underestimate the two strength. Now, of course, that's okay for establishing conservative design allowables, but if we're really trying to understand the ultimate strength and make comparisons about some of the factors which affect it, then we really want to try to get the real ultimate strength. So there's a bit of a debate about how to get the load in. The simplest way is just take a specimen and load it through the ends, as you see in this little schematic up here. But even if you machine the ends really flat and perfectly square, inevitably you will find that they fail from the ends there and the specimen will tend to split. So this type of test method does tend to underestimate the strength. Then you can have a shear loaded specimen where you grip it from the sides, introduce the load by shear, but that does produce high stress concentrations at the end here where the load has to get into the specimen. And so really the best compromise is combined loading, where you load it from the end, but you also have tabs. And in that case there, the tabs take some of the load and reduce the possibility of it splitting from the end. And then the rest of the load in the tab comes out here in the gauge section. But because some of it's coming from the end and some of it from shear, you have a reduced stress concentration. And what you really want to do is to have the minimum thickness of tabs to avoid failure from the ends. And that will give you the least stress concentration at this point and give you the best chance of measuring a reasonable value. Of course, the flatness of the ends of the specimen is really crucial. These have to be ground very, very flat and parallel, and also the edges need to be well machined and need to be very parallel because the alignment is absolutely crucial. And this jig here, which was developed at Imperial College by Jürgen Heiberle some years back, is a good representation. There are other variations on this of how you can get that combined end loading and shear, which probably gives some of the best results for this type of testing. But there are other types of testing, as we shall see later. One is using flexural tests. So if you have a flexural test, then you can avoid the problem about localized failures where you put the load in. And for many composites, you get compressive failure with this type of test, despite the fact that for most materials, if we look in the data sheets, they're supposed to have higher tensile strengths than compressive strengths. There are some times where you actually get a tensile failure in this sort of situation. But for many composites, you do get a compressive failure. And if you have large enough loading rollers, then you can avoid section, you can get a gauge section failure where you introduce the load. And there's another alternative to the bending test where you have some sort of pin end and buckling test. And if the specimen is quite long, it will buckle, and then you'll get a flexural failure in the middle, which will be a combination of compression and bending, but can be largely compression driven. However, there's a snag with this type of test, and that is that actually the result you get depends on the thickness, because it depends on the strain gradient. So the strain gradient affects how much support the less stressed material gives the material at the maximum stress, and therefore affects the results. And we showed this some years ago with scaled buckling tests. So we had a good test here, we got a gauge section failure, and we scaled the whole specimen, including the buckling fixtures. And you can see in this graph here that the strain went up to some very high values. 1 millimeter thick specimens, we got 2.1% strain, which is about twice what you might expect with a more standard test. And as the specimen gets thicker, the strain reduces. So this is a bit of a problem with bending tests and something you have to be very careful about. It's also possible to produce compressive failures in tensile tests on specially designed laminates, and we'll hear a bit about that from Frederic Laurin a bit later. What about the effect of stress volume? I showed some tests which were fully scaled, but the bigger specimens had a larger stress volume than the smaller ones. And since the compressive failure depends on alignment, which is variable, you might expect that a bigger specimen might have more chance of having a worse patch of misalignment and therefore lower strength. I think this has not really been resolved fully yet, but I would argue that whatever indications there are, is it's perhaps less of an effect, certainly in the strain gradient. And in these tests here on these pin buckling rigs, we did vary both the length and the width of the specimens and got a moderate variation in volume, but got very similar failure strains. And it's interesting to note that here we got from these specimens are actually all the same thickness, but with the fully scaled specimens, of course, there's a thickness effect. And that's another question which this really affects more the traditional tests. When you have a thicker specimen, then it's more difficult to get the load in. And so sometimes you may see what looks like a size effect, but actually it's due to thicker specimens being more difficult to get the load into. So other factors which affect compressive strength, it's been demonstrated that ply thickness and the manufacturing method is very important. So thin plies tend to show a higher strength. This is some data from EPFL with some very thin 30, I think this is, what's the size here? 30 grams per square meter UD material, which shows a substantially higher strength than more standard 100 or 300 grams per square meter pre-preg, and also significantly lower variability as well. And this was attributed to more homogeneity in the plies with these thin plies which have been spread. And it shows the potential effect of manufacturing. And of course, if you have significant misalignment, which can arise in the manufacturing, or actually wrinkles, then you can have very big reductions in strength. So this also highlights the importance of having specimens which are representative of the material in the component that you're going to be using to make sure that the tests, the coupon tests, are actually representative of the full component. So what about the factors affecting compressive strength? Well, it's very clear and obvious that temperature and moisture have big effects in decreasing the strength. Here's some data from that Costas Soutis published some years back. Very strong trend both for temperature and also for moisture. And also strain rate is known to have a big effect. And here's some data showing substantial increase with strain rate. Now, we can argue about the actual values, and in particular, this value, the static value here for iron 78552 is very low, but nevertheless, and that's probably associated with some aspects of the testing, but nevertheless, on a like-for-like comparison, you can see that for a large effect like this, strain rate does have a substantial effect. Other stress components, shear stresses have a big effect on reducing compressive strength. That's one of the reasons why these stress concentrations at the grips are so critical, because there's a big interaction between shear and compression. And you see this from the data from Yentl and Fleck, where they did torsion and compression on tubes. And you can see more or less a linear interaction between a pure compression and a pure shear. So there's a big effect of interaction between shear and compression. The effect of the interaction of other stress components is less clear. And for that, we need some better tests. Other factors affecting strength? Well, one thing is hybridization. We've demonstrated that you can get up to 3% compressive strain in thin ply carbon when it's sandwiched between S glass. So here we've got a hybrid where we've got these thin carbon plies between glass. It is loaded in bending, so part of this high strain may be due to the fact there's a bending test, but you can see we've got to over 3% in that carbon before it fails. There are also some indications that the layout may have some effect, and especially when you have a lot of 45-degree plies, that may provide some stabilization for the 0 plies. And modeling also suggests that the stacking sequence may have some effect on strength, although I would say that at the moment there's probably not enough experimental data to really see what that is. And so that brings us back to the point that we need better experimental data, better test methods. And I hope as a result of the discussion we have today, we can move forward, both in understanding how best to measure compressive strength, but also to getting some tests where we can really look at some of these issues and have a better understanding of what does contribute to compressive strength. So with that, I'd like to finish.
Okay, thank you, Michael.
There are some references in that paper, which we will make available later.
Yes, we will also include the paper when we share the slides afterwards, in case you did not manage to get the paper with our initial invitation. So we won't have time for questions right now. We will get questions after all the 5-minute presentations are over. So we will get started right away with Dan Adams from Wyoming Test Fixtures, who can start sharing his screen now.
Thank you. Let's see here.
Okay, we see your screen, not in full screen mode yet.
How's that?
Yeah, perfect. You can get started.
Okay, thank you. And I'd like to spend a few minutes here speaking about compression testing and what I call the pursuit of the best suited test method. So first of all, by best suited, traditionally that has...
Dan, your camera is not on. I don't know whether you were wanting to share.
As I mentioned, I've been having some difficulty with it. Let's
right,
see here. Yeah, I'm going to leave it off for now because it goes on and off and it's a distraction. So the best suited typically has meant the highest measured 0-degree compression strength, and as Michael implied, also getting acceptable failure modes and failure locations. And through the years, this has led the community to do all kinds of different things, some a little bit on the crazy side, but looking to get the highest measured compression strength. And some called it the Mount Everest of compression testing, where getting to the point where the compression strength equals the tensile strength. And the plot that's shown here is just an example of reducing the gauge section further and further, but get to the point where you're just not there. And so where has this led us? Well, To summarize, today, in terms of people that are using compression test methods to get data for material allowables and such, there's really three categories of compression test methods commonly used, and best described perhaps by how the load is introduced into the specimen. So shear loaded specimens, where the specimens are tabbed and loaded through the tabbing surfaces. There's a standardized test by ASTM called the ITRI compression test. And as you can see from the photo here, it's a little bit like loading a tensile coupon in wedge grips. But now the orientation of the wedge angle has been reversed. And instead of having the grip bodies, you have these block fixtures with cavities that the block goes in. And so you're able to generate compressive loading in the specimen. The higher you load, the more clamping pressure that's also been produced. And as Michael said, you get stress concentrations at the end of the tabs. And this has been standardized a long time, since the 1970s. There's also end loading, and there is currently no standardized test method in ASTM. There's a test that's called the Boeing modified D695. You know that perhaps the D695 is for unreinforced plastics with dog bone shaped specimens. That has been taken and modified into a straight sided specimen with tabs similar to the one I just showed. But now the tabbing provides a larger end area, as Michael mentioned, and the specimen is completely end loaded, and you can see those guides that are used to prevent out-of-plane buckling. This is probably, of the three methods that are commonly used, the most common, perhaps because with the very short gauge section and with these so-called anti-buckling guides, you actually get a less of a tendency to get any problems with buckling or out-of-plane deformation. The third is a combined loading. And in this particular case, you apply load both through the ends and the sides. This is a fixture used for doing so. It's basically clamping the specimen between the blocks that increases the gauge area, the end area. And so this is now standardized more recently in 2001. And is commonly used as well. So I would note that I've mentioned only ASTM, and ISO basically has a compression standard that allows shear loading and end loading, including these types of methods. Here's a comparison of the sizes of the fixture. The ITRI is massive compared to the other two, but just to give you an indication of what these look like. So when we speak of the challenges associated with compression testing, it's really all about getting the compression load into the specimen and minimizing all the bad things that can happen. And you can see the list of all the bad things, and then hopefully if things go well, you have a very uniform compression strength and you can get a gauge section failure. Now, one of the things that people have been trying to do now for a period of time is get the community to recognize that you don't have to test unidirectional specimens. And so testing a cross-ply specimen, and particularly using the combined loading compression test fixture, will allow you to actually get compression testing without having to tab the specimens. And so you're basically increasing the thickness of the laminate through the use of cross-plies, not introducing any higher force that needs applied to the specimen for the most part. And again, untabbed specimens. This does require a backout factor, which some people get a little bit nervous about, but essentially the backout factor is simply a laminated plate theory developed way of looking at the load sharing between the 0 and the 90-degree plies. And after all, that's what the tool that we use then to design laminates and analyze them. So the backout factor, as you can see, actually is just a function of the elastic properties E1, E2, and nu1, 2. And for a cross-ply laminate, a backout factor of about 1.8 is used then to multiply the apparent strength of the 090 laminate to get the 0-degree strength based on the laminated plate theory expression there. And this is some accumulation of results. This is from back in the 1990s, but this is now a plot of the backed out 0-degree compression strength on the vertical axis, and on the horizontal axis is the modulus of the laminates that's tested. And all this is now from old data from AS4 3501-6. But way over on the right-hand side, those data points are all unidirectional. Then as you move to the left, the next grouping is cross-ply, zeros and 90s. The next one, about more than halfway to the left, those are quasi-isotropic laminates. And if you look at all that data, you see a lot of scatter, and yet there is a general agreement on the 0-degree ply compression strength. When you move to the further to the left, you see the data points way up that are much higher. Those are sometimes called special laminates, attempts to get higher compression strengths using specially designed laminates. So the takeaway from this is the backout factors and the use of non-unidirectional laminates works well for cross-ply and can be used for quasi-isotropic. So in summary, reasons for using cross-ply laminates are shown: less scatter, elimination of the use of tabs, and classical lamination theory that's used for the backout factor is very well accepted. So this is perhaps a tool now in the pursuit of the best compression test for composite laminates, the use of cross-ply laminates and combined loading. That's all I have. Thank you.
Thank you, Dan. So now we move to Bodo Fiedler from the Technical University of Hamburg. Bodo, you can take over the screen share. Yeah, great. We see your screen in full screen and we see your video.
Okay, yeah, hello everybody. Thank you very much giving me the opportunity to introduce our, I would say, mainly buckling support and how we introduce the load into the composite, unidirectional composite. And yeah, it's for long and thin specimen, and it's very similar. I mean, just as to give you the introduction, why with the problems we faced, you see on the figures, on the pictures on the bottom. So if we use the with the standard setup with the tabs, then we see the delaminations and the break very close to the tabs here. And so even without tabs, I think that's what Michael already said. So allow me very, very brief. So that were our problems here. Brittle failure in this load introduction area. And so then this is the standard anti-buckling device we were using at that time. And for investigation here for fatigue after impact properties. And here is to measure the slit here is to measure, to observe the specimen and to measure temperature and so on because of friction. So this was used before, and now to overcome this problem, we used also this combined loading. So with shear, and maybe I can, you see here that it has two parts, which are an upper and a lower part, and in between is here comes a specimen. Here on the bottom left, you can see it, the black one is a specimen. And then mounted here, and it has in the center area here, this part is slightly lower so that we have no friction. And this is about 100 micrometer lower, or this can be adapted. You can, of course, machine 50 microns. And we decided not to have the end tabs because of the tolerances. So now the specimen is very flat here, and only in this central area there, I mean, before buckling, there's no friction. And if you have only low, you can avoid this problem, minimize that. And we have this window here to record the surface temperature. And here you see how here now the specimen is in blue. And the other point, so we have the load introduction by shear and by the normal load, compressive load, so combined loading as well. And we have, I would say, due to the compression, we have a free contraction, or it's the opposite. So the under compression, the specimen becomes wider, but there's no additional load there. So this has a free edges here for moving it. On the right-hand side, you see how it is mounted on the machine, the setup. And with this configuration, we get really nice failure in the center area of the specimen, and much more cycles we can measure. So the measured lifetime is or cycles to failure are much higher. So this is just a brief introduction of our setup, and I thank you for your acknowledgement, for your attention, sorry, and yeah, happy to answer questions later on. Thank you very much.
Thank you, Bodo. Then we move to Alberto Barroso.
Hi, can you hear me?
Yeah, we hear and see you.
All right. Good afternoon. So
we're not seeing your screen yet, though.
No, can you see my screen? One moment. Screen here. All right. Now?
Yeah, now we see the PowerPoint, but not in full screen. Yeah, now it's in full screen. Yeah,
full screen.
You can
Perfect.
get started.
All right, thank you very much. So I'm Alberto Barroso, and I will be presented with Federico Paris, this study on the influence of the stress singularities in the compression stress evaluation of composites. Taking advantage of the previous introduction, the letter you received for this workshop identifies this problem as one of the main factors of these premature failures in this compression strength characterization. So the presentation I'm having today is just the influence of these stress singularities on these premature failures. For the compressive strength, this configuration from a linear elastic point of view has stresses which are not bounded. The stress field is singular, which is something under discussion. But this stress singular field depends mainly on two singular parameters: the generalized stress intensity factor, which depends on the global geometry and far field loading. We will not study this factor as we are not modifying the global geometry of the sample, and the order of stress singularity, which depends on the local problem, the local geometry of the corner, the local material properties, and the local boundary conditions. So the objective of this presentation is to try to remove or reduce as much as possible, whenever it's not possible to remove, the order of stress singularities and check if this has any effect on the strength of the samples. We will do this analysis in two ways: changing very slightly the local geometry of the corner and the local material properties, of course, of the tab, not of the material being tested. Experimental evidences and the studies with these singularities show that the standard test for this test has this end tab configuration, and if we change this standard configuration to another one, which is more compliant with this reverse chamfer field with resin, compressive strength increases. So the calculations of the order of stress singularities and their influence in this change of the strength, we will not use any finite element or numerical models, because we can perform a semi-analytical calculation to obtain these stress singularities, because they only depend on the local geometry, material properties, and boundary conditions of the problem. So for the standard geometry configuration, what we are going to show, we have developed a tool for obtaining semi-analytically this order of stress singularities, and for the standard geometry that you can see here you have the orders of stress singularities. In the horizontal axis, you can see the angle alpha of the end tab, and in the vertical axis, the order of stress singularities. This standard configuration, the original one, has in this B material corner 3 singularity terms. We just will concentrate on the worst one, which is 0.49, which is very close to that of a crack, which is 0.5. So this stress singularity is very, very strong. For the modifications, we have two different corners. One is a bimaterial corners between the resin and the material. And here also we show the stress singularities in the horizontal axis, the angle between the resin and the material, and in the vertical axis, the stress singularities. For 45 degrees, which is the configuration proposed, the order of stress singularities is 0.09, 5 times lower than the one of the original configuration. To be honest, we can also check if we make a chamfer of 45 degrees, the order of stress singularities for 45 degrees with the tap, which decreases, but it is not so low as this one. For the other corner, which is this 3 material corner between the tap, the resin, and the material, we have also these stress singularities. Just to summarize, one of the local minimums is for 45 degrees of this configuration with 0.22 in the order of stress singularities, which is less than the half than the original. There is another minimum configuration, but this is not practical from a machining point of view because it implies very, very high angles. So the idea, in conclusion, although we have not completely removed the stress singularities, these reductions in the order of stress singularities has led to this incremental strength of the test. So as conclusions, it's very clear. This increment in strength has been clearly influenced by the reduction of the orders of stress singularities in the samples in these end tabs. We have several other experimental evidence of that case, not in compression, but this intention for the bimaterial interface for adhesives, for example, between composite materials and resin, we have increased double strength values, removing the stress singularities in the bimaterial interface. Or for example, in off-axis tension test for the shearing characterization of materials, we can completely remove the order of stress singularities of these corners between the tap and the material being tested, which depends on the angle of the tap and the angle of the fiber. And we can obtain the combination of both to increase this shear strength and avoid premature failure. So I just would like to finish inviting you to use our tool. We plan shortly to be online, but meanwhile, we invite you to contact us if you have problems and you want to calculate this order of stress singularities for your problem. Thank you.
Thank you, Alberto. And that email address of yours is really easy to recognize, to remember. ABC. That's excellent. Okay, our next speaker is Frederic Laurin. Yeah, we see your screen. Yeah, we see your full
can you
screen.
see me?
Yeah, and we hear you and see you. Excellent.
Okay, great. Thank you very much for this kind introduction. So I'm going to present you the work that we have performed at ONERA in collaboration with François-Xavier Izari and Pascal Polny. So in this presentation, we are going to talk about tests in order to determine the longitudinal compressive strength. We are going to analyze different standard tests, such as the compression test, but also alternative tests, such as bending one or another innovative one. So the idea of this presentation is to try to answer to the following question: are the experimental data consistent? Moreover, we are going to talk about, at the end of this presentation, about the choice of the modeling scale. Indeed, we would like to work at the mesoscale in order to be able to predict the strength of large composite structures using, for instance, multi-layered shell elements. But if you observe carefully the failure mechanism, you are going to observe fiber kinking, which are well defined at the microscopic scale. So first of all, I'm going to talk about the test. And we are going to analyze compression test, which are the standard one, but also bending test, which are an alternative to that. And finally, an innovative test that we have proposed recently at ONERA. First of all, I'm going to talk about the classical compressive test. All the experimental data that I'm going to present has been performed on the T700M21, which is a carbon epoxy materials. All the specimens have been manufactured at ONERA. In the present case, we have tested 16 plies laminate constituted only with 0° ply. And we have performed a very classical and standard test, a compression. I have to mention that we introduce the loading by pushing on the edge. We work with very small specimen in order to avoid buckling problem. So we have determined the longitudinal compressive strength, which is equal to roughly 900 MPa. And you can see that the failure pattern is not so great because the failure occurs close to the jaws. And this point has been clearly explained previously. And because of that, we are going to obtain a pretty large scattering into the experimental data. Therefore, we are trying to consider alternative tests, such as bending test on unidirectional ply. So bending tests are relevant for carbon epoxy materials since the longitudinal compressive strength is 2 times lower than the tensile one. Therefore, you are going to fail in compression if you apply a bending test. If you apply a bending test, you are going to avoid buckling issues, and the failure will be far from the jaws, as you can see here on the pictures. What we used at ONERA is not the classical 4-point bending test, because such experimental device induce premature failure under the loading span. Therefore, we use a compression with pivot test, which consists in introducing an offset through the thickness when you introduce the loading in order to generate a pure bending loading into the specimen. And therefore, it allows us measuring the strain on the upper and lower skin thanks to digital image correlation to measure directly the strain during the test. We have performed tests on a 16 plies only with 0° and 32 plies. And you can see that the strengths that we have obtained are extremely extremely high. For the thin specimen, it's about 1,300 MPa, and for the thick one, it's about 1,200 MPa. This strength has been determined considering finite element simulations. It's a bad point because these finite element simulations are not so easy to perform. You have to take into account the geometrical and material non-linearity, and then you are able to extract such a strength. But it is not so easy, such as using an analytical model as it has been done previously. So we obtain very high compressive strength in that case. So finally, we have considered an innovative tensile test. So the idea is the following. You consider a different ply orientation and a 90° ply. You apply a tensile loading, and due to block poisson effect, you are going to generate compression into the 90° ply. And the idea is to optimize the stacking sequences in order to fail in compression. Moreover, you would like to avoid transverse crack prior to the final failure due to compression. So if you use these stacking sequences that we have determined, you are going to obtain a failure due to compression. We have checked that considering SEM analysis or X-ray. And you can see that we have obtained a rather high value equal to about 1,000 MPa and with a very low scattering since we avoid edge effect because the failure occurs at mid-width. So we have obtained a pretty high compressive strength, but the value is embedded between the compression and the bending one. So to analyze that, we have considered a model developed by Grandidier and co-author and defined at the microscopic scale. He has proposed an analytica formula, which is very simple and can be used in design office for aeronautics. This formula has been based on several finite element simulation at the microscale. And this formula can be decomposed in 2 parts. First of all, you try to predict the micro-buckling mechanism, and it is very close to what Budiansky has already proposed, considering the plasticity of the matrix at the microscale. And the second part of the equation is the original part, take into account structural effect. And therefore, you take into account different type of loading, ply position, and ply thickness. In order to fit the model, you need data at the mesoscale, for instance, plus or minus 45-degree tensile test to determine the shear behavior at the ply scale, and also to provide microscopic data, such as, for instance, radius of fiber, fiber ratio, or modulus at the microscale. And if you do that, this is what we have done for the T721. We have then tried to predict the strength for the different configuration of tests that I have presented previously. The tensile test on the stacking sequence is very specific, and the bending test performed on 0-degree ply constituted with 16 ply and 32 ply. And what you can see is that the predictions are in very good agreement with experimental data, and we describe the trends that we have observed experimentally. So to conclude, the microscopic scale seems to be very relevant to predict the fiber kinking which occur at this scale. And moreover, the test data that we have generated in bending and in tension, thanks to our very specific test, are consistent. So thank you for your attention.
Thank you, Frederic, for the interesting presentation. Now we move to the next speaker, which is Hao Cui.
Hello.
Yeah, we hear and see you. You can share your screen.
Yeah.
Yeah, we see your screen, not in full screen mode yet.
Yeah. Shall I start?
Yeah, now we see it in full screen. You can start.
Right, okay. Thank you, Yentl. Good afternoon. My name is Hao Cui. I'm from Northwestern Polytechnical University. Today, I would like to start my slides here by first talking about, our understanding on the field mechanisms in terms of fiber kinking mode. When we look into the field mechanisms here, we know, it is generally agreed that the interfiber shear stress here is a key, and it is introduced here because of the angle between the fiber and the loading axis. And this interfiber shear will causing crack between fibers and then resulting in instability and then buckling at a microscopic level, which triggers the fiber kinking. If we agree with this fact, then we have to consider or take into account the interfiber shear stress in the formula when we calculate or when we analyze the fiber compressive failure. And the thing is, the interfiber shear stress, it can be in plane or it can be out plane. It can come from many different ways. For example, here at the bottom left corner, when we load even a uniaxial laminate at an off-axis angle, then what you will see here is significant amount of in-plane shear, the tau 1,2 involved in the laminate. And if it is a multi-directional laminate, then it gets more significant because inevitably there must be some fiber that is not aligned with the loading axis. And on top of that, we also have the interlaminar shear stress as well, the sigma 1,3 or tau 1,3 in a multi-directional laminate. So the interfiber shear stress or the shear stress in general has to be considered when we're trying to analyze the failure of practical composite structures in engineering practice. And if we agree, we have to take into account the interfiber shear stress, then it leads to the question that is UD sample the best solution for measuring the fiber compressive strength? Because you may argue that the UD laminates cannot represent most of the composite structures because they are all multi-directional and they inevitably have this interfiber shear stress of different ways, of different altitude, of different level. And what makes it worse or more difficult is, the testing of uniaxial, of unidirectional composite laminates itself is very challenging and problematic. Here is like a chart we prepared like back to 1 or 2 years ago, trying to summarize the fiber compressive strength obtained from different configurations. And you can see there's, even up to, more than 100% difference between one to another on the single same IM7-8552 material. So in my opinion, I think maybe as Dan has already mentioned, maybe, the cross-ply limit or multi-directional limits can be a better way and maybe an easier and a pragmatic way to characterizing the fiber, the loading capacity, let's put it this way, of the laminates when it's bearing, longitudinal compressive stress. So what we have done recently with colleagues from University of Oxford is, we loaded a cross-ply laminates, as you can see here, at different off-axis angle. In such a way, we can, have different combination of longitudinal compressive stress and in-plane shear stress, which makes it possible for us to get an envelope at different ratio between shear and compression. And also, it has been shown to be very simple and robust. And we even recently loaded it at a velocity of, I think, around up to 6 meters per second, enabling a full characterization of the failing envelope at a high loading rate. And here we can clearly see how the failure envelope is changing depending on the shear stress level and the loading rate. So that's why I think maybe, instead of testing UD laminates, a off-axis compression test of cross-ply laminates may provide a bit more reliable and accurate information regarding when the crack may initiate in a longitudinal compressive loop. However, I would like to finish my presentation here by saying, okay, if we consider defects and fiber misalignment, some residual stress as part of as manufactured laminates, then shall we consider using tools like friction mechanics, damage mechanics to considering how it propagates? Okay, thank you very much.
Thank you, Hao. So our next speaker is, oh wait, I have to check myself, is Xun Wu from the University of Bristol. So Xun.
Hi, thank you, Yentl.
We hear and see you.
Can you see me now?
Yeah, just the screen share hasn't started yet.
Yeah, so just trying to put them on a full screen.
Yeah, we see your screen, not in full screen yet.
Yes. So is that okay now?
I do not see it in full screen yet. Yeah, now we do. You can get started. Thanks.
Yeah. Thank you, Yentl. So, hi everyone. I'm Xun Wu, a research associate from the Bristol Composites Institute, and thank you for giving me this opportunity to present my work on the compressive failures of unidirectional carbon fiber composites from bending test. And this work was being done with Professor Michael Wisnom. So as Michael mentioned previously, the compressive strength of the carbon fiber is so hard to measure. Actually, they are always find very low and cause some premature failures or had a large variability in this testing through this testing method. So that's why there's so many different testing methods has been developed. Some of these shown on the screen is some very standard one, and there's also more like modified one or more advanced one available in the literature. But we hadn't still actually getting to the bottom, how to get a proper or a reliable compressive strength measurement. So today, my presentation will be only focused on this flexure testing method because it got a very high and more consistent compressive measurement, and it does not require very high precision and complex machining. At the same time, they have some disadvantage so far. First, it failed in premature failures under the loading nose, and also it got the strain gradient enhancement effects, and also the set effect in the bending is hard to quantify. So the key challenge of this work is to understand separate size and strain gradient effect in this bending test, and to develop such a method to get more reliable compressive strain allowable. So the first part of this presentation is trying to avoid this kind of premature failures under the loading nose. So first of all, we're using some ASTM standard suggest the diameter of the loading nose 10 millimeter, and I will test this 5 millimeter beam in the bending. And all the beams has been consistently failed under the loading nose position. And also it brings a very large coefficient of variation in the beam. If we take an interactive specimen after this peak, first load drops here, and we can actually see the damage was initiated at this contact area between the loading nose and the specimen. So we make a little bit effort and to increase the diameter of the loading nose from the 10 to 25 millimeter. And in this case, we see the consistent gauge failure in compression in all the specimens. And at the same time, we got a higher compressive strain, and also the coefficient variation is significantly reduced. And the second part of my presentation will be focused on how to investigate this strain gradient effect in the bending beam. And we use a sandwich beam method. So we use this carbon and wood sandwich beam, and we keep the gauge section dimension the same. And also we keep the thickness of the carbon skins the same, which allow us to have the same volume in highest stress across all the testing. At the same time, we vary the depth of the beam from the 6 millimeter to 38 millimeter, and we change the strain gradient. So as you see from this red line, if the beam is very thin, the strain gradient in the carbon is significantly large. But with the increase of the thickness of the core, we can see the strain gradient in the carbon is reduced and reduced. At the same time, in order to maintain the similar applied load, we increase the support span, and also we select the large roller diameters in this case as well. And the core material we choose is an ash wood rather than the honeycomb has been given in the standard, because it gives a high shear strength and it's easy to machine in different thickness. So here is the result of the strain gradient effect. So if we plot the compressive strain with the total beam thickness, we can see the strain, the compressive strain measurement is reduced with the increase of the beam thickness. And actually the strain gradient effect is especially significant with the beam less than 10 millimeter thick. But from the 10 millimeter above, there's a very little effect of the strain gradient, as you can see here. At the same time, we got a very low coefficient variation and consistent results. And all the beam has been consistently failed in the gauge section in the compression of the sandwich beam in all 4 thickness. We also compare of our results with some previous one in the literature. So this is the IM78552. So first we compare with the combined loading compression. And this one shows like a very low values and a large coefficient variation. And with some more recent and advanced like modified dog bond compression prevented by the Hao, they have a very nice set of the compressive strain, and also the coefficient is very low, it's only 2.8%. And our result for this carbon and wood sandwich beam, it gives even higher compressive strain and at similar coefficient variation to Hao's results. So this brings us a conclusion is this carbon fiber and wood sandwich beam with a core depth larger than 20 millimeter, which is super recommended for the compressive measurement in the future test. And that's my presentation. Thank you very much.
Thank you, Xun, and thank you for sticking exactly to the time limit. Our next presenter is Lars Mikkelsen from DTU.
Yes.
Okay, I see and hear you. And we see your desktop. Yeah, and full screen. You can get started.
Yes, thank you. So I will just make a pointer here. Yeah. So so my name is Lars Mikkelsen. So I'm from DTU Wind Energy, and I take actually a case here which are relevant for the wind energy issue, and actually many of the modern large turbine blades now are considering using protruded profiles, and protruded profiles is one I'm standing with here, is typical a highly unidirectional carbon fiber composites with a thickness of maybe 5 millimeter. So in order to actually test this and find the properties both regarding compression strengths, but also compressive fatigue is a challenge. I will send my acknowledgement also to my colleagues, Anthony, Tom, Jakob, and Ulrich, which have done a lot of this work also, and Konstantinos, which is a master student, which have done some of the modeling in the end. So as I said, it's you could say a high quality material with high fiber content. So we have fiber volume fraction above 60%, nearly 70%, even for glass fiber. Cases for pultruded glass fiber, we have above 70% also. We can find this fiber volume fraction by burn-off test. We can do a fiber stiffness, composite stiffness comparison, and we can also do SEM-based, so scanning electron microscope segmentation. And based on that, we get, you could say, consistent values of fiber volume fraction of this, and we can also see how the fiber volume fraction is varying. Typical for thinner pultruded profile, we may have higher fiber volume fraction compared to the thicker one. Here's an example on a 5 mm thick composite. So here's a small cutout, 2 × 2 mm, where we look into the fiber alignment, and we also have a high degree of fiber alignment with a standard deviation of fiber orientation on between 1.5 to 2.5 degrees typically for this kind of composites. And there's 2 references down here where you can find some of the data for this. So the test method we are using here is a mechanical combined loading fixture. The benefit of this is that we can keep, so the way it's working is that it put on load both at the end and a shear, and it keep the same, a constant ratio between the 2 load values during a fatigue cycle. So this is one of the, you could say, one of our aim is to be able to do fatigue testing in compression. We have, so you can find a little old reference for this picture here. We have improved this, and we can now also work with different aspect ratio between the end load and the shear load on our sample. And here's a typical test sample for that. So this rectangular shaped test coupon, you can see that to the left here. We have observed that based on a pre-preg study that there can be some dependency on the thickness. So here is made different pre-preg with different thickness based on the same UD carbon fiber composite. And we can see that for thin cases, we have a lower value, maybe due to some buckling issue. Then we reach a certain rather high value. And then if you get thicker laminates, then we are decreasing the compression strength again. So when we now talk about protruded profiles where we have the sample size thickness of around 5 mm, then we may have an issue of using this test geometry. So this is the reason that we now have played with, you could say, you could either machine the composite in a thickness direction or in a width direction. And we prefer to do the wasted in a width direction in order to avoid introducing failure in the thickness direction, especially during the fatigue loading, and also that the material may not be constant through the thickness. So have a representative of the full thickness of our composite. So this is the 3 cases we have looked at many different cases, but here's the 3 I will present, and we can see that there are a relation, say, going from the left to the right, that if you narrow the gauge section here in a width direction, then we get higher values of the strengths. But first, I will actually also show that we also see that the stiffness is decreasing when we have, we say, this more narrow region, and this may be due to that for this wider sample, then there will be some constraint in the width direction. So it will not be purely uniaxial compression stresses here, but there will be some Poisson's ratio effect giving apparent higher stiffness, which may also influencing the strength value. We can see also that the tensile or the compression curves are bended, and in some ways continuing the bending of the behavior in tension. So the failure behavior for the wide sample is end failure. For the little more narrow one is splitting, and for the most narrow we have a failure in a gauge section, but also splitting of some of the samples. So not a perfect solution still. The last slide I will show is that, of course, we also like to understand the mechanism controlling this. And we know that compression strength is controlled mainly by the fiber orientation and then the matrix properties, so the stress strain curve for the matrix properties. So the failure mechanism is very different from tension. Tension is controlled by strain to failure of the fibers, but in compression it's more the shear loading in the matrix which are supporting the fiber, while the fiber is most misaligned. And this is included in this final model, the effect of this, by introducing the stress strain curve for the fiber and the matrix, and then the fiber orientation distribution in the material. And by this, we are able to predict the stress strain curve for the composite in compression. And it's based on a nonlinear rules of mixture, you could say, incremental rules of mixture for a composite. So thank you very much.
Thank you, Lars. Then we move on to Christian Hochard. And then afterwards we'll have one more presentation from Costas Soutis. So Christian, we can see you. And we see your slides, not in full screen yet.
Yes. Is it okay?
Yeah, you can get started.
Thank you. I will present you the effect of matrix degradation and the compressive strength in fiber direction only for simple specimens. The case of structures with stress concentration is presented in the PhD of Aldo Cocchi. The effect of matrix degradation with respect to temperatures has been widely studied. Here, for example, the drop of the strength with respect to the temperature without thresholds. The effect of the matrix damage due to mechanical loading corresponding to small cracks parallel to the fibers on the compressive strength is less studied. It's a subject of my presentation. We proposed a first procedure to get this effect using 0.90 tubes in fatigue torsion, generating shear stresses in the plies and shear damage. Here you can see the evolution of the shear stiffness during the fatigue torsion loading, and of course increasing of the shear damage. After that, we can load the tube in traction here. Here you can see the decreasing of the strength for very high level of damage. Or in compression, here we have the different stress strain curve for different level of damage. You can see that the strength decrease progressively, but the stiffness is the same. The problem with this technique is realization of the tubes. For tension tests, we use for a long time hourglass shaped specimen, which assure failure in the middle of the specimen and low stress gradient due to the large radius. In place of the standard geometry for the end compression test with anti-buckling fixture, we propose the same kind of hourglass geometry with the largest possible radius. with this geometry. Here is an example of test. We have got better strengths for glass fiber, for example, here, compared to the standard geometry. To test the effect of matrix damage, we propose another procedure. This procedure uses very +45, -45, very large specimens loaded in fatigue tension, and of course generating shear stresses in the ply and shear damage. Estimation based on strain field measurement. Then we cut the specimens, hourglass-shaped specimen in the fiber direction and loaded it in compression here. Here, in the case of glass fiber, we have the decreasing of the strength here with respect to the damage, with something which is less progressive compared to carbon fiber. So, in conclusion of our work, we have shown that compression strength in fiber direction decrease with the matrix damage. It seems that the threshold in compression is very low compared to the threshold in traction here for a very high level of damage. And it seems that the evolution of the strength with respect to the damage is different depending on the type of fiber, glass or carbon fiber. So thank you for your attention.
Thank you, Christian. And then we move to our final speaker, Costas Soutis.
Let me unmute first.
Yeah, we hear you.
Then
we
show my
you.
face.
Yeah.
Then share my screen. Wow, which one am I going to share with you today? And thank you so much. Can you see? Yeah. Can you see my screen now?
We see your screen. You can start.
Brilliant, brilliant. What can I say? What can I say? You covered everything. I don't have to say much. We've seen that factors affecting the UD compressive strength. Obviously, the constituent material properties and interface are very important. They make up your composite. How you make your composite, fabrication induced effects have a huge impact on what you are measuring. Test standards, we have to follow test standards where they exist. Specimen design, test fixture, and instrumentation of paramount importance. And the guy who performs the tests, skills of operator, vital. Environment has an impact. Hot, wet, cold affect the properties of what you are measuring. The type of defects you expect to get when you fabricate your laminate, they come in the form of voids, resin-rich regions, ply undulation, fiber misalignment, which is different from fiber waviness. They come up for different reasons. And all of this contribute to the triggering of fiber microbuckling, which is a fiber instability failure mode. Test methods, fixture and skills of operator. Test method, test fixture, specimen alignment in the testing jig. And skills also affect the measurement, ultimate stress value. Test standards are important, provide detailed specimen preparation, specimen design, test fixture, properties to measure, how to measure them, what kind of instrumentation you need, and what are acceptable failure modes. Failure modes, whew, so critical. There are ISO standards, ASTM standards, there are crack test methods. Oh, Imperial College of Science, Technology, and Medicine have their own standards. Airbus have their own standards. Boeing have their own standards. So the test method describes the way the load is applied. And we've seen from early presentations, direct end load and shear load, mixed, combined load, sandwich beam, 4-point bending. And of course, analysis. Analysis helps specimen design and to estimate the likely performance of the composite before making it and before testing it. So test standards, they guide us. We've seen earlier some of the well-established test fixtures, the E3 combined load. Oh, the modified Celanese. Now, if you go to Instron or MTS, they can sell you the modified Celanese. And the typical size of the specimen, which has been calculated based on analysis, is 110 millimeters long, which 50 millimeters is the tapped area, 10 millimeters gauge length, 2 millimeters thickness. So as you can see, the width of the specimen is about 5 times the thickness, and the length of the specimen for carbon epoxy systems is 5 times the thickness. Specimen design. Why do you need end tabs? You need them because they effectively transfer load from the test machine grips to the specimen, and they provide an adequate restraint against specimen buckling and brooming. Nobody spoke about brooming. And the overall specimen stability needs to be sufficient to ensure that compressive failure occurs significantly before potential buckling. You try to avoid Euler buckling. So you need to have the correct combination of specimen length and flexural stiffness. And you remember, you try to achieve a uniform, uniaxial compressive stress field in the gauge length of your specimen. So you cannot have a specimen which is too long, and you cannot have a specimen which is too short. Because if the specimen is too short, then obviously you get another damage mode, which gives you a reduced stress, ultimate stress, which is not representative of the intrinsic strength property of the composite. And where the traditional test jigs might fail you is that when you would like to test much thicker specimens, you have to create specimens that they are 8 millimeters thick or 25 millimeters thick, which it implies that they have to be wider and they have to be longer. So you need high volume value load frames. So for instance, to break the 2 millimeter thick specimen of a carbon epoxy, you need a test frame load cell of 25 to 30 kilonewtons. If you want to break this one, the 8 millimeter thick, you need 200 kilonewtons. So it changes the game. And the modified ICSTM test jig, where 90% of the load is transferred by end loading and the 10% by shear, it allows you to test under the same kinematic boundary conditions and the same loading conditions, small size, medium size, large size, excessively large specimens under the same configuration. And then when we look at what we measure and we look at how the specimen has failed, modern polymer composites, we have seen that they fail mainly by fiber microbuckling, fiber instability damage mode. That gives you 30 to 40% lower ultimate stress than in tension. Now, if you look at earlier systems, and if you look at the data by Ewins and Ham back in 1973 and Ewins and Potter a bit later in 1980, you're going to see that those high strength or high modulus carbon epoxy systems, they were failing mainly in the fiber shear mode, where actually what you were measuring, it was very close to the tensile strength, because anyway, by convention, the compressive strength should be the same as your tensile strength. Well, of course, this is not the case with modern composites because of the waviness, because of the softer resin, because of so many reasons. So you can see the transition from fiber shear mode to buckling mode. In those days, it was happening at about 100 degrees Celsius. While in my system that I tested for the T894C some, long time ago now, 30 plus years, at room temperature, it was fiber microbuckling, which you can see on the right-hand side there, the typical fiber microbuckling. So in that system, in order to get close to the value predicted by, say, the equal strain model and approach the sigma f VF value, you have to test at minus 50 degrees Celsius. So what we learned from today is that in order to evaluate structural integrity of composite components, we do lots of mechanical testing. And everybody's familiar now with the pyramid testing there. But I believe that the pyramid of testing can be replaced in many occasions by the pyramid of modeling, where you develop understanding. And eventually, of course, it is not going to eliminate your testing, but it's going to reduce the number of tests you need in order to characterize the structural integrity of your component. Thank you so much.
Thank you, Costas. And so this is our last 5-minute presentation. Now we move into the panel discussion. So I ask all the panel members to switch on their cameras and unmute when you want to speak. So who wants to get the discussion started?
Yeah, can I start off the discussion? And I've got a question for Dan. Very interesting work on the cross-ply laminates. I wanted to ask you about the back-out factor and the effect of non-linearity in the fiber direction. So do people take account of that non-linearity in the fiber direction in calculating the compressive strength of the zeros? And sort of a related point is, well, what about the strains? Because you can directly measure those. And have you compared strains with cross-plies and other test methods with UDs?
So to start with, the back-out factor, I showed the expression for it, and it is basically just related to the elastic properties. And I don't think there's been anything. I'm going to turn off my camera because it freezes up. I don't think that there's been a lot of work going beyond the basic back-out factor from classical lamination theory. And so, what was the other part of your question?
Well, so I think it's interesting. It would be very interesting to compare the results with taking account of the nonlinearity, because you showed some very high values for specimens which didn't have many zeros. And part of that may be related to nonlinearities. I don't know whether that's the case, but very interesting to look at that. But the other question was, well, you can directly measure the strain. Okay, measuring the strength, you've got to back it out with some sort of factor, but you can directly measure the strain. And I was just wondering what sort of values of strain you get with those cross-plies and how they compare with what you would get with a 0-degree UD.
I see, good point. And that slide that I showed, that was a collection of values and from lots of different studies throughout several years. It would be very interesting to correlate some of those effects with the strains, failure strains. I'm not aware of that ever being published, so that would be something very interesting to go back and take a look at.
Thank you.
I think you do have to be careful if you want to measure strains on such short gauge lengths. That's not always that straightforward. It may not even be uniform. Okay, and any other comments from the panelists?
Can I add a comment on this work, and maybe I'll show you graphically something that I would like to share with you probably and see if it adds value. Let me see. Can you see my screen?
Yeah, we can see a pyramid.
Oh, sorry. Oh, I cannot move it. Let me see. Yes, here we are. This is kind of work that Dan tried to show us. Here we have tested lots of multidirectional laminates where you have a uniformly distributed layup, and the layup is plus 45, 0, minus 45, 90. It was work done with Michael Wisnom some years ago, investigating size effects, scaling effects. And you're going to see that actually the compressive strength of the unidirectional lamina is, unaffected by, and you can recover it, you can back out the strength of the 0-ply, which is actually very close to what we measured in carefully designed specimens where they were entirely 100% 0. Of course, other things are happening when you have blocked layups. Yeah, but that's, we can discuss that as more questions are coming up. Does that help?
Well, so
Michael?
you're saying that the strains are similar in the quasi-isotropic
Correct, correct.
and the UD.
Correct.
I think is, but because I think this is a crucial question, actually.
Yes.
Is the strain the same in a laminate and a UD? And particularly with the cross-plies, I think we've had from several presentations, we've had cross-plies look very promising, but can we be sure that the strains are the same? Now, when you've got 45s in there, arguably those 45s may help to stabilize the zeros. They don't appear to be from what you're saying, but I think there's still some more work we could do on that.
Yes, and we can see that the scatter of the data, and here each point there, as you can see, there are at least 8 to 10 specimens, not one specimen. We get a bit higher scatter when you go to the thicker, much thicker specimens, which there again, it's more difficult, harder to actually, probably you have to look at the lamination process and the cure cycle and post-cure cycle, because obviously you use the same cycle as you do for the all the other laminates. Maybe you need to do something different, more pressure, I don't know. And consolidation.
Costas, how was this measured? Which testing method was used here for these measurements?
The test method is no debuggling devices. The specimen has been designed not to buckle and not to fail by brooming. And we followed the Airbus compression test method.
Yeah, because I think in a lot of this type of data, it's often difficult to identify whether it's because they didn't fail properly, whether it's due to stress concentrations, or whether the effects you're observing that they are real.
I have images to show you that all fail within the gauge length.
Yeah, that's very reassuring, I think.
And the laminate, all the laminates were fabricated by Airbus.
So I'm just interested in this is which material? Oh, this is T800. Okay, all right. So you know what the strain is?
It's about 1.1%, 1.16, very similar to what we measure for the UD. This is published data.
Yeah.
Okay, Lars?
Yeah, I have a question regarding this, using this multi-axial layup. How about the stress field in a UD that cannot be uniaxial compression stresses anymore when you have off-axis oriented fiber around it? So will that lower or higher the compression strength of the UD when you have constrain a material for deforming in a twist direction?
Probably you can say, as Michael explained, that it's probably that's like your debuggling device in the zero laminate. So you can say you have some kind of lateral support, but your behavior is dictated by the fiber instability in the zero plies. Now, if you laminate, you start growing edge delaminations and growing other secondary damage modes, then it's going to be a different story. But for this system, and that's what we spoke earlier about damage mechanisms and dominant damage modes. And we've seen it with the work with Ewens and Ham and Ewens and Potter. You have transition of mechanisms. And if you get other damage modes, matrix cracking, resin cracking, splitting, debonding, edge delaminations, then obviously your stress field will be affected. You're not going to have any more dominant 1D compression.
And I think also one of the issues you can have with these quasi-isotropic layups is, as I think Michael showed either in the paper or in your presentation, that if you have a shear stress on top of the uniaxial compression stress of something like 30 megapascal, you're already seeing a reduction in the compression strength that you're expecting. I don't know what the typical levels are that you create with this type of layups, but they're probably not zero.
but it appears that they don't affect, while the other one, the blocked ones, they do, and we know the reason.
Yeah.
But since you haven't asked, I'm not going to tell you.
Any other comments or points to discuss? Yeah, Federico.
Yes, thank you,
Then
Yentl. As in the first dummy workshop we had with reference to tension, I have contacted several companies to check how they see this problem. With reference to the companies that performed the test, I'm talking about 30,000 in the last 3 years, something like this. They say they are desperate with this test because this test forces them to have to follow at least 3 standards with 3 setups and 3 ways of introduction deloading, which lead to many failures in validating test results and obtaining different values of XC depending on the procedure followed for the same material. But I would add that I'm more concerned about other things because, for instance, Michael showed the variation with the thickness of the specimen tested. For instance, with a grammage of 30 was much higher than with a grammage of 300. But now, what happens if I get the value from a 30 grammage and then it is used by someone having 300? Okay, it's on the side of the lack of security. Also, the presence already mentioned of the influence of another stress is terrible, because if we send people the information that this is the value of the strength and they use in a situation where there are many stresses involved, it's not safe. So now, to conclude, I have contacted with the companies that use the values we produce, and they said we don't trust on the values. So when I have an actual laminate very thick, we only trust on the results obtained from the thick laminate. We have performed lot of tests on this because they don't trust on the prediction obtained from the values that we got from a simple specimen. That's what I wanted to say. Thank you.
Okay, thank you, Federico. I think it's also interesting how the assessment of the industry is different for tensile strength and for compression strength. With tensile strength, I think the main conclusion was that, yeah, it's lower than it probably is in reality, but they're actually quite happy with that. While here with compression strength, they seem to be much more concerned. That's an interesting observation, how it's different for tension and for compression. I would propose that we have a short break here of 10 minutes, and then I'll give the word to Hao, who also wanted to raise a point, and then we'll open up the discussion towards the audience as well. So we will return in 10 minutes at 3:45 or 4:45 or whatever time zone you're in about 10 minutes.
And you can put your questions on the Q&A now, if you like, while you have them, and we'll answer them later. Thank you.
Yeah, indeed, you can already put them there, and then we'll start with the ones that came in first. Okay, see you again in 10 minutes. I hope most of you are back. I see that Michael has restarted recording. That's excellent. So I will first give the word to Hao, who still wanted to make a remark, and then we'll open up the floor to the rest of the audience. So go ahead, Hao.
Thank you, Yentl. So I would like to follow in the conversation like between the UD and the cross-ply laminates. Like, also I noticed comments from Michael saying like we cannot pursue a perfect test. Like, because I very much agree with this. And when we look into the difference between a UD and a cross-ply laminate, what I'm thinking about is what is the fundamental difference between them. At a microscopic level, the interfiber shear stress is certainly affected by neighboring plies, cross-ply limits, right? And it also provides this lateral support or constraint to enhance its stability against the local buckling. So yes, I mean, for a cross-ply limit, I guess to some degree, the fiber compressive strength, let's put it this way, or the failure stress must be different from a UD laminate. But the next question is, which is a more representative terminology or value for industrial application? Because there's very little application where we have UD thick limits, and if you see looking around, and most of the composite structures are multi-directional, either it's an airplane or a satellite or rocket. And there, at this microscopic level, they all have the same feature or similar feature as when we are testing a small dog bone sample or any STM standard samples with quasi-isotropic or cross-ply laminates. So that's why from this point of view, I guess a cross-ply or quasi-isotropic layup is a bit more one step closer to what the industry needs, although it may be not perfectly reflect the most intrinsic fiber kinking failure strengths. But I guess it's more applicable and pragmatic, let's say, in describing and using this terminology for analyzing the failure of composite structures under longitudinal compressive stress or load. Yeah.
I can just respond. I completely agree with you. I think what we care about is multi-directional laminates, but I think we haven't yet answered the question, is the strain the same? Or if it's not, what does it depend on? How does it depend on the layout? Because you could also have the situation where you overestimate the strength because you happen to have a lot of 45s or I don't know what. So what we really need is a fundamental understanding of what controls compression, and then models whereby we can look at the effect of different lamination sequences if they have an effect. That's my view.
Yeah, I second the opinion of Michael. It's not because in practice you will mainly have multi-directional laminates that measuring the longitudinal compression strength isn't important. If you want to know what the effect of adding 90 plies or adding 45 plies is, you need to know what that reference pure 0 degree strength is to be able to study it. And it seems that this is still a really big issue to measure that accurately.
Yes. So if I can just challenge Costas for a second, in one of your papers many years ago, you showed laminate which had a lot of 45 degree plies and it had a significantly higher compressive strain than the other stacking sequences. Have you got any comment on that?
Yes, that was the Royal Society paper, wasn't it?
I don't remember. I did reference it in the short paper.
Yeah, I mean, as I explained earlier, it behaves the off-axis plies. They provide the lateral support to the 0 layers that they carry your uniaxial compressive load.
Yeah. So doesn't that go against your argument that those quasi-isotropics were the same as the UD?
It's not because what it does, it enables the 0 plies to reach the intrinsic strain, if you like, in the mode of fiber microbuckling. Can I show you one slide?
Up to our chair.
Okay.
Yes, please.
Okay.
Briefly.
Let me try to share.
And then afterwards we'll move to audience questions.
Yeah. Okay. Can you see the screen?
Yeah.
Okay. I mean, people use Budiansky and use Argon and use Rosen, and those models they're there for the post-buckling behavior once the fibers are broken. And that's why that expression, it doesn't explicitly have the modulus of the fiber, the diameter of the fiber, the strength of the fiber, all the stuff related to the element that actually carries the load. And we've noticed that the critical damage mode is the fiber instability damage mode, the fiber microbuckling, which of course, in the case of Ewings and Ham and Hughes and Potter, they didn't have that fiber instability mode. It was appearing, the transition was at 100 degrees Celsius from fiber shear mode to fiber instability damage mode. All right. Now, here we can see a simple expression which explains also the constraining effect of the off-axis splice. And only they become damaging at the free edge. Depends very much on your layup, and we have also data, experimental data for, as Michael says, 0 plus minus 45 orientations and off-axis orientations. And it all depends on the interlaminar shear stresses that you have at the free edge. And if those interlaminar shear stresses are damaging and they introduce additional waviness to your already wavy fibers, then you're going to see that in order to trigger that instability damage mode, this stress, the critical stress that triggers fiber microbuckling, is going to be affected. And here, before we have breakage, fiber breakage, you need to know at what kind of stress that mode will appear. And that it depends very much on your modulus of your fiber, the diameter of your fiber, the initial waviness, not misalignment. Misalignment is additional, it's off-axis, 0 plies, yeah? The interlaminar shear stresses, the non-linear response of your resin. So this shear modulus is not the elastic modulus, but it varies with the applied displacement. And this is what affects the stress at which the instability damage mode is triggered.
Michael, do you want to respond to that?
No, I think we should move on and have some more questions. Yeah, thank you, Costas.
Okay, so everybody in the audience, you can please ask your questions in the Q&A section of Zoom, which should be quite convenient to use. There is already one question there, and there's also a question or a suggestion for elaboration from the chat, but I'll first go to the question from Anton Shipsha. I'm not sure whether I'm pronouncing that correctly. This is a question or a comment directed to Michael. Do you want to respond to any part of this? I think everybody can also see this, right, in the audience and the panelists.
I really need to look at this paper. It looks interesting. Well, I don't quite understand how the matrix tensile failure affects the compressive failure load, but if you've got some good test data, I'd be interested to look at it. But I don't have any other comment really at the moment. It's just very, I think because of all the problems we've been discussing, I think it's very challenging. So we have to look very carefully at the data, and I'll be interested to look at that.
Yeah, I agree. Okay, then maybe what I will do now is, there was a question from Michael Hinton. I will give you permission to speak if I can find you in the participants list.
Michael Hinton is still around?
Very much so, yes.
Wait, I'm just having trouble to get him, to give him permission.
Don't give him permission. No, don't give him permission.
Wait,
lock him
Michael,
out.
can you give him permission to?
Just...
yeah, Michael, I think you need to do it because I'm not co-host yet.
I beg your pardon. I'm sorry. So
yeah, that's why I can't do it myself.
Okay, I've given it. Mike, you should be able to talk.
Good afternoon. Can you hear me?
Yeah.
We cannot see you. Put your camera on, please.
That's
not
going to be possible.
My gift, Costas, and
we would like to see facial expressions.
I'm not sure it works. We're not encouraging the cameras.
Yeah, I think it's not possible in this setup, to be honest.
Oh,
Go
thanks
ahead,
God
Mike.
for that, so we don't see his face.
Just imagine, Costas, that I've just outrun you because I can do that, and that will be what my so here's my question. So as some of you know me, it's good to be with some friends. I'd like to put a bit of a challenge here because frankly, really interesting set of presentations today, but it's a bit like how many angels want to dance on the top of a pin. I could be sitting here in 50 years' time, there'll still be discussions going on about the perfect test. We're now, I don't know, certainly 50 years into my career when this was all being done when I first started. So let's just turn the problem the other way around. And Federico made some comments about it earlier, and I think some of you on this call have made the same comments, which is, in the real world, engineers are trying to design structures. In the real world, they take these basic properties from the standard tests as a starter for 10. And then they're trying to actually make sure that they build structures that work, that you can manufacture and perform. What we've got from this community over the last 10 years is a lot of understanding of some of the fundamental mechanisms and the interactions and so forth. And it'd be great if we can codify all of those so we can start from, I want to build this component. It will look something like this potentially. It will possibly be manufactured in this way. So now let's work backwards to say, how can we predict what the strengths ought to be so that we can then come up with realistic design allowables? So it's turn the problem the other way around is really what my plea would be. And there's a great project there waiting to be knitted together by this community. I shall stop there. Thank you.
Anybody
Well, I
want to
certainly
respond
agree.
to that?
I certainly agree with you, Mike. I think that's absolutely right. And we need to move on. We don't want to just focus only on these test methods, but I still maintain that it's important to have a sound basis, because if we don't have a solid basis on which to move forward, then we may get something which ultimately may not be as useful. But I take your point, and we should be considering that as well as getting to the basics of what controls the failure. So,
that's
yeah.
fine. Thank you very much, everybody. Thank you.
Anybody else wants to comment on that further?
I've got another question, actually. I'd like to ask Frederic about his very interesting tests. So in your tension test, then what about the effect of transverse tension and possibly matrix cracks that might affect the strength of your 90 plies?
Yeah, that's a very good question. Indeed, in the specimens that we have designed in the stacking sequence, in the 90-degree ply, we have not a pure longitudinal compressive stress. We generate also a tensile transverse stress, sigma 2,2, which could be very high. And the point is that we have tried to design the stacking sequences in order to avoid that. Obviously, for instance, if you use thin plies, it will be easier because the strength of the thin plies will increase as you decrease the thickness of the ply. But we have not a pure stress state, pure uniaxial stress state to measure the strength. And the question I'm not able to answer to that is there a real interaction between sigma 2,2 in tension and sigma 1,1 in compression, considering the fact that there is no damage, I mean, prior any transverse crack. If there is transverse crack, the story is completely different. Christian Auchard has demonstrated that experimentally, if you have cracks, the property of the matrix will be decreased, and therefore the buckling of the fiber will be easier and you are going to fail. And in some cases where we have poorly designed our specimen, transverse crack occur and buckling, the fiber buckling starts, and we obtain very low value. So the point is critical, but the question I have is, perhaps someone has the answer. I don't know if there is a strong interaction between sigma 2,2 and sigma 1,1, sigma 2,2 in tension and sigma 1,1 in compression. I've started a collaboration with Jean-Claude Grandidier. It has been mentioned previously by Costas Soutis. If you work at the microscale, you can try to understand how the round ply will affect the local state of state. Jean-Claude Grandidier has already published a paper like that, but I haven't seen a paper in which he clearly demonstrates sigma 2,2 and sigma 1,1. So I've seen Costas Soutis who wants to
go ahead, Costas.
add a comment.
Okay.
Go ahead.
Well,
you want to share a slide again?
Yes. I want to share a slide again.
Yeah, we can see it.
Yeah, no, just a moment. Here it is. Now you're right. Here now you can see the second layup is blocked layup. Yeah, so you have lots of plies of the same orientation together. So you have got lots of zeros there. And what we're going to see is that this is the laminate where this is an X-ray when it came out from the autoclave after it's been manufactured by Airbus. And this is the laminate where the plies are uniformly distributed. And then this is the laminate before you apply any load, where the plies are blocked. And this is the thick one, the 8mm thick ply level scaling, where you go and cut your specimens. You can actually hear, you don't need acoustic emission. You can actually hear all the matrix cracking that goes crazy and it takes place. And then when you test those specimens, yes, in the presence of your matrix cracking, look at what happens to the strength of your laminate. It dropped from 650 to down to 288. And this is their interaction of mechanisms. Yes, of course, it affects dramatically the stability of your zero plies that they carry your uniaxial compressive stress at the uniaxial compressive loading. Yes. Fascinating stuff.
Yeah, so very interesting. And I remember on the work we did together years ago, we got similar effects with edge delaminations coming as a result.
Exactly, where you have the central open hole and the specimen didn't fail from the open hole, it failed from the free edge.
Can I just have one more question for Frederic? And that's, it was very interesting, the work you did with showing with the Grandidier model. And I'm just wondering, what does that say about the thickness you need to get rid of the strain gradient effect, and whether we can correlate that with the results that Xun showed for the strain gradient effect?
Yeah, that's also a good point. In the presentation, the picture is very small, but he has tried, based on the different finite element simulation performed at the micro scale, to generate some guideline. And therefore, you are going to consider differently if you have a pure compression or if you have bending with the strain gradient through the thickness. And the thickness of the plies that you are going to introduce into the model depend on the strain gradient. And they distinguish two cases: if you are close to the middle of the thickness, or if you are close to the edge, because the strain the strain gradient could be different. And in the bending test that I have presented, I used the condition with bending for the outer ply, and it fails pretty well with the experimental data that I have. So clearly, for the work presented by Xun Wu, where you change the thickness of the core in order to change the strain gradient in the model, it will affect the hypothetic thickness of the plies that you are going to introduce into the model to predict the structural effect into the equation. So it is integrated into the model, but it has not really been validated from an experimental point of view with different strain gradient as you did. So it could be a great test cases for such an approach, which is again very simplified in order to be transferred to a design office. Because now an engineer wants a strength at the ply level to design a wing, and we say that you have a fiber kinking and you have to work at the micro level, and you need micro data radius of the fiber, and it's going to afraid everyone. So the point is that we have to determine a fair trade-off between the scale where things happen and the scale where we want to model things to consider large composite structures. And that's typically something very difficult And very excited about the work performed by Jean-Claude Grandidier. He tried to perform such a trade-off with some limitation, and we have to go further, but I think it's a critical question for compression. The question of the scale, the working scale, the modeling scale and the experimental scale is not so obvious, and that's clearly a point on which we want to progress.
Any follow-up remarks on that? Yeah, Costas.
Just to make a comment, because obviously the Airbus designer is not going to base his design on the actual UD lamina strength. Usually they will operate with open hole compression, and more likely in hot wet conditions, which dramatically reduces the compressive critical stress value. So, and that's why at the end their design currently is kind of conservative, accommodating all the uncertainties that we have in our failure criteria and in our modeling. But the modeling remains of paramount importance because it helps you to understand mechanisms, interactions, and interfaces and properties of the constituents that you put in your soup. It's vital. Can I ask also a question for Lars? Because Lars kept very quiet today. He presented to us some large structures that probably will please Michael Hinton, because that is a real part, a real structure, a real component. And Lars kept very quiet. Lars, can I ask you the question? Why do you perform UD compressive testing when actually most of that part experiences kind of more multi-axial stress field and more kind of flexural loading, which introduces, of course, in-plane stress as well? But
actually, you could say you have those two spark cap, and you have an aerodynamic load which are bending the blade. So on one side you have purely compression nearly, so compression with some fatigue over that, and the other side you have tension. The main reason for putting in the carbon fiber is to increase the stiffness, so making the blade longer. So all blades which are longer than this 75 meter, now the blade is up to 110 meter long, and weight around 50 to 60 ton for each blade. So there are including a lot of carbon fiber in that, but it's in order to give a higher, say, bending stiffness. But of course, we should also be able to carry. And then the issue is that compression strength is lower than tension strength. So if you compare compression and tension, then for this specific pultruded profile, then we are measuring only 60% in compression compared to tension. So the design criteria is mainly in compression when we talk about the static loading.
When it fails, when the component fails, does it come close to your ultimate compressive stress that you measure?
No,
because other critical modes will take place before you observe fiber instability or fiber microbuckling.
In principle, you are far away from the static strength. So it's mainly fatigue life we are considering. But over the lifetime of 20 years or 25 years, then you may have, you could say, degrading material, and then suddenly you may rely on some compression strength of some element. I have actually a question to Michael regarding because bending, I can see, is when we have a carbon fiber composite which are weaker in compression than in tension, then of course the obvious way to measure that is in 4-point bending. Also for solid carbon fiber profiles, because for thick laminates, then it's very hard to make sandwich structures because the load gets so high, and the load introduction is nearly impossible. We have tried that, but it's really hard to introduce the load into the structure when we have 5 millimeter protruded profile carbon fiber on each side. So the question is, how is it well understood the relation between the strain measured on the surface of a solid UD composite and then the tensile strengths, the compression strength of that?
So I don't think it's well enough understood that you could do a bending test and extrapolate. Okay, we've got some models, and Frederic mentioned Jean-Claude Grandidier's model, but I think at the moment it's would be perhaps a bit risky to extrapolate. But actually, you can do a bending test on a quite big specimen. So you can do a bending test on a 5 millimeter composite. You can either stack them together and make quite a thick specimen, and it does take quite a lot of load and needs quite a long specimen, but it can be done. Or you could put one of those protrusions on a sandwich beam. So yes, the loads will be high and the specimens will be larger, but on the other hand, they'd be more realistic of the sort of situation in a real component. So I think it could be done.
I want to give the word to Michael Hinton. I think you should still have the permission to speak live.
Yeah, okay. It's just a follow on from the comment from Costas and Lars, which nearly went into the right place, but didn't quite. So it's a while ago now, but I did quite a lot of work on protrusions. And so I cut lots of protrusions up and looked at them. If any of you on this call has ever done that, you'll see a whole raft of interesting structures with knots, with swirls, with all sorts of things in them. So again, we're back to what does the real structure look like?
Yeah, Lars, I guess you want to respond to that first?
Yeah, and that's actually, you could say, now I've shown, we say, idealized or a nice region of the protruded profile. But what is of major interest for the industry is how cheap can they buy the protruded profile? How fast and cheap can you make them? How much do they accept of strengthening inside the protruded profile in order to still have something which are not failing in fatigue? So definitely that we do not have purely UD, but due to that, in some way our starting point is to get the values for the idealized UD, and there I think a protruded profile is actually a rather good case, because there we have a very idealized UD without nearly anything else, and the fiber is very aligned, even more aligned than the pre-preg. Pre-preg, you are limited. If you try to lay up plies in UD, then you may have a few degrees off axis between the different plies, and that is often not the case for protruded. At least the one we have compared, we have more is more aligned in a protruded profile than pre-preg between the plies, not inside one ply, but between the plies.
Anybody else wants to comment on that?
Watch out for the knots.
Yeah, I mean, we have seen that, Mike. Yes, there's a high variability, and that's part of the problem. Yes.
If nobody wants to comment on that further, Michael Hinton also asked a question in the Q&A. We can try to address that one now, which is essentially about that we've been mainly talking about carbon fiber-based materials, even mainly pre-preg based materials, but there is quite a lot of other material, and I think it's a valid comment. Certain things for in glass fiber thermosets will be different than in carbon fibers. There's also a specific reference to Kevlar fiber composite, which is again a whole different situation, and then laminates based on thermoplastic matrices. So I can perhaps comment on Kevlar fiber thermosets, because we have tested that in our lab and we actually failed to test them properly. They are incredibly difficult because they yield in compression rather than really failing in the traditional sense. And then they buckle much more easily, because when they start yielding, they lose essentially compressive modulus. So you get into buckling issues. We haven't tried the the type of test setup. So you have anti-buckling guides. I guess that would be more appropriate if you want to test Kevlar fiber composites, but in shear loaded compression, yeah, we were not able to test them properly, essentially. Anybody else wants to add to non-carbon thermoset based prepreg question?
I would just say that it depends on the failure mechanism. So yes, as you say, Kevlar's got a completely different failure mechanism. Yeah. So it needs to be treated differently, but glass and many thermoplastic composites have similar sort of kink band mechanisms, in which case the same sorts of issues arise. But actually that leads me to a question I had for Costas, is you showed a plot where you had a low temperature T800 924, which was on the cusp between a microbuckling and a fiber failure. I just want to ask you, did that specimen actually fail by microbuckling or not? Because it was right on the cusp of your graph.
It was definitely much higher than the instability damage mode. It was closer to the fiber shear mode. And that's why.
Did you look at the specimen? Did you look at the micrograph of the failed specimen and see how it actually failed?
No, because we didn't have at that time. We didn't do extensive analysis in that area because you had to do tests at very low temperatures. It was hard to get values of strain and do all this stuff and examine the specimen. But definitely it was closer to the high end rather than the 1600 that we used to have at room temperature. But definitely there, it needs some work. But they work with Yunes and Potter in 1980. They have data, extensive data and micro images where I used one of their schematics to demonstrate the fiber shear mode in their report. Although the report is the Royal Aircraft Establishment, and maybe Mike Hinton might have access to that. I might have it in my office somewhere in the box. But yeah, it's fascinating stuff. I was really pleased that as long as you can control the damage mode, you can get closer to the intrinsic properties of your system.
Any follow-up remarks on that by anybody?
Hi, Costas.
Yeah.
Can you
How? Yes.
Hi. So can you clarify further regarding, let's say, what is the intrinsic failure mechanisms?
No, I didn't say intrinsic failure mechanism. I said the intrinsic property.
Yeah, intrinsic property. Yeah.
Yes, and in this case, so of course you don't have a monolithic system. You have a heterogeneous system. You have a matrix reinforced with fibers. All right. Yeah. And what I'm saying here, the intrinsic strength of that system you have created, yeah, the value that you get for the ultimate stress comes close to your VF sigma F. Yeah, which means it depends entirely, yeah, on the amount of fibers you have and the strength of your fiber as material, as monolithic material.
Costas, but there is one problem in that approach that assumes that you know what sigma F is, which is an incredibly difficult to measure property as well.
Correct.
Theoretically, absolutely right, true. But in practice, it's quite a different story.
In theory,
you've seen the slides that you encouraged me to take out of my talk because it was analytical, where you try to demonstrate and validate simplifications and assumptions you make in your model. Doesn't matter how sophisticated or how simple it is. Yeah, you then create a system where you think that once you manufactured it, satisfies the conditions that you try to simulate. And if you go back to that plot, you're going to see that we have selected in that case a soft matrix in the form of copper, reinforced with very brittle, strong fibers, tungsten, where we managed to when you plot your equal strain model, all the experimental data fits nicely. And if you go and magnify, you're going to see from that data, you get the V minimum, the V critical, and the V maximum, because once you exceed it, it means that you can't wet your fibers and you get premature failures. You lose the strengthening effect that you tried to achieve in the first place in your composite design.
Lars, you want to respond to that, I think?
Yeah, because I think about this intrinsic properties when we talk about, and now in some way, I think fatigue is, of course, we don't get the same failure mechanism, but fatigue is a good way, at least for fatigue, to see how failure develop in the material. And if you do tension fatigue, then we can see that the fiber begin to break, and that will break out into the structure, and then they will fail in the end. In compression, we also have been looking for internal failure or damage evolution, and the only thing we can see in pure UD is that there are coming some small matrix cracks in between the fibers, shear cracks, which are, of course, I think the understanding is that if you have a very misaligned region, then we have a more shear loading there, and this shear loading will generate some small cracks will develop, but we have not really been able to go very far in that path, because suddenly then it just fail. So it's really hard
because you need to go to test at minus 50, minus 60, because you have soft resins, and the engineer has selected soft resins because his design is not strength based, it's not stiffness based. He cares about the toughness. He cares about damage tolerance. He cares about damage resistance. He cares about all these other things. Where you have to compromise your design.
But it's also instability problem. So it is when we are reaching this instability issue with the fiber alignment. So suddenly the fiber will king out at a kink band.
Exactly.
And this instability is different from, you could say, is often you could say controlled also by boundary condition and the thickness. Often we will have kink band in the thickness direction, not in the width of our laminate. So there are some things which are affected by, you could say, also the boundary of our laminate.
Correct. Because in Ham and Potter's system, they had thicker fibers as well, which it means that the mismatch of thermal properties in the matrix and the fiber, the thermal stresses, they were not high enough to introduce waviness that we are facing today in a 5 or 6 micrometers fiber diameter. Yeah. And and we go back to Michael's comment that he made when Mike Hinton asked his question, is that we need to understand those fundamental concepts, and then only then we can help the designer to gain confidence and say, this is important, this is not important, this happens in those cases, this doesn't happen in those cases. And in Lars' case, in his big structure, there will be much earlier events that will take place, so the fiber will never experience that strength, whatever he measures in tensor or compression. But still, still he didn't tell us how the German supergiant turbine failed, that tower. How did it fail? Was it a sabotage or was it structural? Bad design?
I don't know.
What do you mean you don't know? You have no comment, no opinion? Lars, you are the expert. Were you involved in that?
No.
That is going to be an amazing case study for your students.
Costas, perhaps one aspect that I want to comment on. I think it is really important for us to help people who do structural designs of airplane wings, turbine blades. But I think we also should not forget that we can help material developers, like resin developers, interface developers, and that I think is much more with micromechanical simulations. And I think we have to support both aspects. I think so far we've mainly talked about the structural design, but that's really not the only thing to help the industry with.
I agree.
I have a small comment to that, because actually you could say the main interest regarding also compression strength is maybe not from the wind turbine blade industry, so is is even more from the material suppliers, because there is going out and investigate and make better materials, and we need to have test methods where we can judge whether one material is better than another, and it's not that one is better to fail in shear than the other one in a gripping region. So we need to be able to improve the material by that. So the material supply, we should help them to make better materials.
Yeah, I guess Costas wants to speak again.
I would like to intervene and share this comment, because Yentl did some very good comments there. Here you can see everybody's familiar with the Ansky model, which of course is based on the Argood model, which is what of course started with the Rosen model. Now, if you could go and manipulate a bit that simple equation that gives you the compressive stress as a function of shear properties of the matrix and initial and fiber misalignment, and manipulate it a bit, you're going to see at the end, it gives you a fractional increase of the yield shear stress is 2 times as effective in rising the critical compressive stress as is a similar increase in the shear modulus. And the same is true for a fractional reduction in fiber waviness. And these are coming from very simple models, but they have so much information that the micromechanics guy can work with the chemist and tell to the chemist, you know something, for the pre-micro buckling stage, I need this and this and this. Once the fibers break, actually, I would like to have this and this and this. I don't know if you can achieve that as a chemist, but I think he knows more chemistry than us. So I think, yes, I agree with Yentl there that we can play a role in the design of the composite system. Of course, much of that information is, critical to the material manufacturer, and they don't tell us anything about interfaces and all this stuff.
Just to further comment on this, I think you see this in nearly all the compressive strength micromechanical models, that they focus on misalignment as one value. In reality, it's much more complex. They don't follow sinusoidal paths that are all sort of in phase with each other. A real microstructure is way, way more complex. So I think that is also something we just don't understand and we cannot capture in models at the moment.
No.
And then we will also get more realistic ways of capturing the effect of the yield stress and the shear modulus and so on. There is another question from Mike Hinton on specifically related to the space sector and how they extract design allowables. Is there anybody on the panel who wants to respond to that? This is primarily about very cold environments. Or is there anybody with some expertise in that specific area?
I would say we have regarding the temperature. Is that the temperature dependency you're aiming for cold or hot climate? I think
Michael can respond to that. Or Mike.
I'm just trying to I'm trying to just prod some discussions within the community here. Yeah. And just one thought is that as you will know, the matrix materials used for space applications is significantly different from that used for aero applications. And of course, they're operating in a completely different environment. Yeah. So it would be interesting, hence my question, to understand any of the lessons that have been learned with characterizing those materials and how that information gets carried across into design of satellites, etc., for orbital structures. Yeah. If there's nobody on the call with the expertise, we won't get anywhere.
Frederic?
Just a comment. Indeed, we have to learn from space industry, especially in aeronautics now, because they try to use liquid hydrogen for propulsion, and tank that we are going to use will be extremely cold, and we will be faced to the same problem. The tank, due to the pressure, you will be a part in tension and a part in compression with a very cold environment. Therefore, the matrix will be very stiff. It will affect the compression, And moreover, this is also another question into the chat, considering the thermal residual stresses. When you are going to decrease the temperature, you can generate cracks only due to the thermal loading. And if you have cracks into the matrix, you are going to dramatically decrease the compressive strength, as it has been presented previously by Costas Soutis. So clearly, we are faced today in aeronautics to cold environment due to the introduction of hydrogen, liquid hydrogen as a propulsion solution for future aircraft. So we currently work on that, but again, compression is not simple. And now with very low temperature, I mean, very, very low, we will be faced to lots of practical challenges, especially for the experimental device. We are going to be to have a dilatation coefficient very different from the composite one. And we are going to be faced to that in order to avoid to introduce parasite straight off test, especially at the end of the jaws. So it will open a new field today that we are going to be faced, especially in aeronautic industry, not only in space.
I think Lars wanted to comment as well.
Yeah, I think at first we have tried to use you could say by changing temperature during the testing, then this is a way to change the matrix properties without actually changing the other parameter in the composite. So this is a good way to extract what is a dependency of the matrix properties, also something Norman Fleck have done for many years ago. And then the question is also because we are using new resin system, and often they're looking a lot on more ductile resin system, also thermoplastic material, for example. But that may be good or bad for compression strength of compression fatigue, depending on whether it is the micro cracks or the ductility which are governing the failure, compression failure. And I don't think there's one answer for that. Also for cool climate cases, is that good or bad? It can be both.
The critical thing, as mentioned, is that's coming at us really quickly, like right now. So there's another great challenge for this community, isn't there?
Mike Hinton, even before you go to space, we have to think of the hydrogen storage tanks, since hydrogen started becoming kind of an attractive alternative zero emissions fuel.
Yes.
And I'm talking about hydrogen storage tanks, not for space, but for cars, for other applications down here on Earth.
Yeah, but they split into two camps, as the community I'm sure knows. One is containing liquid hydrogen at -252 degrees C. The other is containing gas under pressure. And obviously, both of those are very much in play at the moment nationally.
Yeah.
We already touched upon this a little bit, but you've seen the question from Mahmoud Chokri on residual stresses and that they should be taken into account or into consideration in many of the tests we do if they are not just pure UD. So is there anybody who wants to comment on that in more detail?
Already we commented very briefly, and I showed the images of what thermal stresses can do, which can be residual stresses, can do to load carrying capability. Obviously, if you don't account for them and they're large, then they can cause resin damage, matrix damage, which then can lead to instability of fibers and premature failures.
But in principle, shouldn't it help when you have for the pure UD composite? Then when you have shrinkage of the resin, that will you could say that will delay the yielding of the matrix during the compression loading afterwards. So that may be, you could say, helping the compression.
Some beneficial, yes, absolutely, absolutely. But you have to account for them if they become, if they're there and they're high enough.
Any other remarks on this point?
Yes,
Yeah, with reference to your comment about residual stresses, we have found that they are very important in mechanism of failure involving stresses normal to the direction of the fiber. And sometimes they can play a very important role postponing the appearance of damage. So if we think about a mechanism of failure that may appear in situations of under compression, and they involve mechanism of give a role to the stresses normal to the fiber, I'm sure that it will play a significant role. I would like also to say something about the general discussion. We cannot ask people that design component in Airbus of any company, to think in terms of micromechanics. In fact, the person responsible for design of composite in Airbus Spain, now retired, was also a professor in the School of Engineering, and he said, micromechanics is a fantastic topic to deliver a lesson in the school, but it's absolutely useless for a designer of an aircraft. It is true in the sense that when they now have to design something, and due to the fact that they don't have reliable methods, simply in terms of the properties, values of a property, what they do is just testing. We have performed 200, 300, 400 different testing of components or simply when they modify something. I think our role is to understanding the mechanism of failure. And in my opinion, this can only be done at micromechanical level. The main problem is that even when we understand the mechanism of failure, it is not easy to go up to them to say, okay, my understanding lead you to take this into consideration. In the same sense, Yentl, you said we can improve the design of the material. You are absolutely right. I agree with you. The problem is that when we have gone to a company, there are not too many, asking them, can you do this for me because I think this is going to work better? They don't care. Nothing at all. But obviously, if from this meeting we would be able to make some conclusions today or in the next weeks, and from this it is derived that we can ask the manufacturer to do some modifications to improve the properties, it would be fantastic. I would be very happy of the results of this particular meeting.
Okay, Hao, you want to respond to that?
Yes, thank you. I would like to say, following on the comment from Federico on the micromechanical studies. Let's say also the intrinsic property, like Costas mentioned. So as we now agree that at a macroscopic level, the fiber kinking failure can be affected by many issues like fiber misalignment, like the plasticity or nonlinearity of the resin, and also the thermal residual stress and actual. So, which means all this leads to a question: is a single stress value sufficient to describe such a complex nature in this failure mode? Do we need to have a lot of conditions, like at which level misalignment, which level shear stress, whatever, and then this is the specific compressive stress? Or maybe my question is, maybe we should need much more data.
Yeah, I think you're absolutely right, Hao. And I think in the workshop on definition of strength and on tensile strength, we discussed that issue in much more detail. Like size scaling effects, to some extent, they also exist in compressive strength measurements, I think. And then you can define it based on the the characteristic Weibull parameters. So you can then define rather by one parameter, you have to define two parameters. It does get significantly more complicated in that case, of course, perhaps too complicated for an industrial application. But we as academics, of course, have to deliver the understanding to implement these things properly in higher level simulations and predictions. Lars or Frederic?
Yeah.
Lars?
It was actually the you could say discussion on this how to report the measurement values. In tension we have, we say the strain to failure because it's for UD because it's mainly controlled by the fiber failure and therefore it's believed to be a good value to use. And then that is why independent on the fiber volume fraction, because we would like to have something which we are coming with a new composite, or we just manufacture the composite a little different, and then we have other fiber volume fraction. So in compression, I suppose also we should have something which are independent on whether we have which achieved 60% or 65% fiber volume fraction. So we don't need to test for all possibility. So is that clear how to do that, or yeah, in compression?
Frederic, you also wanted to respond to that?
Yeah, it's just a comment considering the remarks performed by Hao Cui. The point is, today, my understanding of the micromechanical interest for an industrial is to say, what is the first order of magnitude and what could be neglected? For instance, the difference between bending and compression, it's huge. So you have to explain it with micromechanical and perhaps to generate some numerical ABAC. And then when you are an engineer, you say, okay, I'm going to perform a bending. Therefore, I'm going to consider in the model such a coefficient depending on the strain gradient. I mean, compression, I will do that. I don't think we are going to find the unique perfect value. I think we have to generate ABAC thanks to micromechanical approach. In some cases, we are going to say, okay, if you just change the order of the two adjacent ply, it's not a big deal. Or perhaps it could be different, and it could be a way to improve your stacking sequences for compression or bending. I think thanks to micromechanical approach, we can help for the design and try to provide some guidelines. But I'm not sure we can go further than that.
Okay, thank you, Frederic. I see Costas wants to respond, but then we are gradually going to wrap up. So go ahead, Costas.
Just, I would like to ask Dan Adams, are you still there? Do you have your second coffee by now, or your third coffee?
Still here. Second
excellent,
coffee.
excellent. So you kept quiet throughout the discussion today. Do you have to make any observations, comments, suggestions, reactions, the American point of view?
Well, I'll tell you a little story that
yes,
I only had 5 minutes and I took 7 before. But so back when the combined loading compression test method was standardized by ASTM, this is in 2001, leading up to it, part of the standard was how to actually back out the 0-degree compression strength from not multi-directional laminates, but just cross-ply laminates using the approach that I discussed. And in fact, it was, you know, there was a lot of push to get the cross-ply laminates in there. But ASTM being the organization that you have to satisfy everyone, I mean, it's a total consensus organization, basically it didn't happen. There were detractors, people that just felt uncomfortable, and it never went through. And I've been, I'm very active in committee D30, and I've brought it up several times through the years.
I served on that committee several years.
Yeah, so there's been a lot of interest, and people are doing it anyway. In fact, if you look at some of the databases that are out there and you really dig into where the compression strength comes from, and these are values people are using, they're from cross-ply laminates for the reasons that I described. And so I've asked the D30 people about why don't we put it back into the standard? I mean, it was never in there other than in drafts. And I think I've got some I think it's going to happen. I think it'll probably be a standard practice that follows the D6641, which would be for unidirectional laminates, and then there'd be a standard practice on how you would modify the test method for using cross-ply laminates and how to do the backout factor. And I think once that happens, you're going to see a gradual but a progressive shift towards going from unidirectional laminates into cross-ply. Going to quasi-isotropic, I think, is going to be a little bit more of a question mark, and I'm not so sure it's a good thing to do, but I agree with Michael that I think that we do need to try and study this and have better answers to questions that come up as we go forward. But I just did want to tell you that I think, first of all, it's being done. And secondly, I think the standards will begin to come around to allowing at least cross-ply laminates. So
excellent, excellent.
So that's an interesting point. And yes, as you said before, I think the effect of non-linearity will be an interesting thing to look at as part of that. But can I just ask a related question to Hao? Hao, you showed some cross-ply results, but actually, if I remember correctly, they were lower than some of the UD results you had shown on the previous slide. Can you comment on that?
Yes, it's a very interesting observation, actually. So which just shows how complicated, the fiber compressive strength can be. Because from my point of view, I think this artificially high, let's put it this way, artificially high strength from this UD laminates may be probably because of the high lateral constraint, which bring in this hydrostatic pressure into the matrix. And because, the resin matrix or the implant shear, even at the microscopic level, is very sensitive to the hydrostatic pressure. And which, whenever there's this hydrostatic pressure, the shear yielding stress is increased, which maybe increase the measured compressive strength ultimately.
Okay, I think we should gradually start wrapping up here. Is there anybody who wants to make a general conclusion on what we have learned, where we should be heading next?
Well, let me just start with saying one thing. For me, this issue about cross-splies versus UD and multi-directional laminates, I think is really a crucial issue, which I think we need to understand. Is it the same or is it different? And if it's different, what did it depend on? And now we've seen several presentations where we've got some interesting methods for getting improved compressive strengths. I'd like to see some really good tests where we look at what the effect of the different layups is on the strength and really try to bottom that one out. That to me is the most significant thing that's come out of this discussion.
Anybody else wants to follow up on that? Yeah, Frederic.
Just a small comment. We talk about the test in order to obtain the highest value of the strength, but I think it's very important to have in mind that we would like also to master as best as we can the scattering, which is due to a bad boundary condition or things like that. And we have seen lots of presentation where we try to master as best as we can the boundary condition to really measure what is the material and not what are the defects into the boundary condition. So the question is, what is a good test? It's not only the highest value, but also a master scattering, which is very important for our industrial partner, since they are going to use the B value. So the average value minus the scattering multiplied by the number of tests. And if you perform just few tests, the decrease will be very high. So we have to generate this trade-off, high value and master the scattering. And I think the simulation will help us to improve the test, mainly to better master the boundary conditions that we are going to apply to our specimens.
Yeah, I think it's indeed true that it's standard deviations or the scatter in the data is really important, but I would also want to stress that this idea that the highest possible compressive strength is probably the most reliable one. I think you also have to be careful depending on the complexity of the test that you are using to measure it. if we start talking about having to back out the contribution of the 90s, and if you don't do that very carefully, you could potentially get higher values than you have in reality. So higher is not necessarily better, although it probably is very often ends up being better. Costas or Michael Hinton? See.
Yeah, shall I go first?
Yeah, go ahead.
Just a bit of a reflection because you're trying to wrap up. We're having a really interesting discussion looking at how progress is being made with testing. Over the same period, over the last 10 years, we've now got carbon fiber aircraft flying across the world. So just bear in mind how the industry is moving forwards with the subject. And so really the challenge for this community, for all of us, is how do we take the learnings that we've got and actually help the industrial use more quickly as they move forward through the need to deal with net zero and a complete transformation of the platforms. So that's the challenge, because we've got lots of learning here, and it'd be really good if we could start to codify that in some way. And I'll leave it there because I think there's a really good opportunity to do just that with the community. Thank you.
Thank you. Anybody else? Costas? Or...
Yes.
Yeah,
I would like to thank the organizers. Amazing meeting. We had some impressive presentations. We had discussed coupons, components, whole structures. And we did have some young people today presenting and be present as well. And Xun Wu gave a very good presentation, some amazing results there that probably will learn from that data, and maybe Lars can communicate again with Xun Wu and see how she can contribute to his blade, especially with those 4-point flexural testing. And yes, it was great to see you all. We have to carry on the good work, and because there is a carbon fiber aeroplane flying around the globe, it doesn't mean that it's really optimized, and it doesn't mean that there is no further work to be done in order to reduce the cost, manufacturing cost, fabrication cost, the drilling, the repair, the recycling. Recycling, good grief, what are we going to do with all those aeroplanes and with all those wind turbine blades, Lars? But there are some amazing applications where 75% of the towers of the windmills can be recycled because it's metal. Yeah, the tower, the whole tower is metal. The only thing that is carbon fiber and glass and composite is the blades, which is about 17%. Lars, am I right?
So,
the content, the composite content in your towers, the windmills.
Yeah, but if you look at the LCA calculation, then the blade is really a small amount of the
small amount. So I gave them 17%, but let's assume 17%. And then you say, what am I going to do with that?
Yeah.
And in Denmark and in Sweden, they came up with some amazing solutions. They cannot recycle it, but they can refabricate it, they can reuse it, and they have already built playgrounds for the children, and also they have created some sheds to keep the bicycles dry.
Yeah. But then we need to make a lot of them in order to use all the turbine blades. So I think we should think about something else and how to reuse it or just scrap it in a proper way.
That's not environmentally friendly. We cannot do that. We can't scrap it. We have to recycle it. We have to find ways of recycling it.
Yeah.
And currently in Manchester, we have an EPSLC funded project where we have developed a room temperature chemical based solution where you dissolve the resin which you can recycle, and you can recover the fibers intact, which is amazing. But more work needs to be done to scale it up.
Okay. I think a very interesting discussion, but we are getting slightly off topic. Maybe we should have a workshop on recycling of composites. Certainly very interesting.
Michael, who said that we have solved all the problems because the aeroplane flies around in carbon fiber.
Anybody wants to comment further on the general conclusions and next steps? I see Michael still has his hand raised. Or is that still a leftover?
Yeah, it is, but I might as well comment. Thank you, Costas. It's always fun. Maybe here's two thoughts, because you asked the question up front, what might be a follow-on seminar be on? One could be, what are we looking at in terms of characterization methods for recovered fibers? That could be one thing. I'll just put that there. Because they are going to be appearing, as Costas said, and we need to think about the test techniques as to whether the current ones that we've been debating are fit for purpose. And a second topic that I'll put there is, what about three-dimensional composites? And I'll leave it there for you to think about. Thank you.
Okay, perhaps just in the last few minutes, whether there are any comments on the topic of the next workshop. So I've mentioned that our current idea is to do this either on shear strength or shear strength measurements, or on transverse tension and compression, or a combination of the two. Are there any comments? Anybody who already knows who would like to contribute there, or thinks that's a bad or a good idea to go for those two topics?
Please put it in the chat as well. If other attendees have got comments on that, please put them in the chat now before we close.
Yeah, very good suggestion. I also see in the meantime there's two more questions in the Q&A, but there are more comments, and we don't really have time left anymore to address them directly. So you can still read them. I think they're very valid and useful comments. Any comments from the panel members on the topic for the next workshop that we'll be organizing?
I personally think
I'm thinking about fatigue is also could be a properties, but of course it's a large field, and how to do proper fatigue testing is something which are related a little to the static, but there are other challenges, especially now when you talk about compression and tension, then when you talk about compression tension fatigue, which are really a challenge, and actually a really present challenge, because that's something which are required for wind turbine blades to be tested in that, because you cannot use this end loading like you do in compression, static compression, and you cannot use the long sample as you do in tension. So for that, how to do this properly, that's also a problem. But it's maybe more related to wind turbine, because that is where the fatigue is I think of most important compared to other.
And I think some of quite a lot of the aspects that we've discussed in the tension workshop and this compression workshop about static loading is also applicable to fatigue, but the fatigue has some additional issues on top of all of those. Costas, do you want to comment on this further?
No, this is we can carry on the good work. All the suggestions are good and attractive, and but obviously we have to take into account the opinion of our audience, and I hope once you collect the results, you might have the answer as well.
Yeah.
Fascinating stuff.
I think the in-plane shear will be one of the very interesting topic as well, because it's very challenging if you consider the pressure dependent, the influence from a fiber rotation, etc. And what is maybe more challenging on top of this in-plane shear is the out-of-plane shear, because that looks to me even more problematic.
Yeah. I think the clear conclusion from this workshop and all the others, either the one in the past or the ones in the future, is that there is no easy test to be performed on composites. I think that's the most obvious conclusion. So thank you very much for your input on that. There's also some comments in the chat that we'll take into account. And I want to conclude here, since it is 5 o'clock UK time now. We will be sharing the slides and the recording in the next few days. Once we've had the chance to upload the recording to YouTube, we'll get in touch. We'll also send around a survey to get some input, some further input on the next topics for the workshop. And then I just want to thank the panelists in particular for their contributions, and obviously also all our audience members. We had approximately 100 people at the peak time, which is quite impressive. So it seems that the community appreciates these workshops, and hopefully they will continue contributing to the community when they're uploaded to YouTube. Thank you very much, and hopefully see you at the next workshop.
Thank you to you.
Thank you.
Thank you for sharing it.
All the best.
Federico. Thank you.
Thank you.
Bye.
Goodbye.
Bye.
Bye. Bye.